This paper focuses on modeling and characterization of a potential bladder-based orthotic device to mitigate shoe slip. The device takes the form of a rubberized shoe sole separated into air bladders. Valves allow bladder deflation via the weight of the user such that the impact of the user's foot with the ground creates a momentary spike in friction coefficient to mitigate slip. Modeling of the system begins by analyzing the various forces acting on the shoe and the human system. For simplicity, the human is modeled as a large mass M1 and the shoe is a very small mass M2. The figure on the left depicts a free body diagram of the various forces in the model, and the figure on the right shows a simple schematic of the potential device. The forces included in the analysis are the rubber compliance of the bladder walls, characterized by post-buckled beam models, coulombic friction, airflow and bladder pressure, and contact mechanics. Understanding airflow behavior is critical for design of the device. Faster airflow creates greater impact forces, increasing the friction coefficient during impact and therefore increasing slip mitigation. Airflow is modeled using a piston cylinder model, air pressure is calculated using the ideal gas law, and flow is calculated numerically using standard head loss equations. This leads to a guide for selecting valves and tubing to create the desired impact upon deflation. A 4-bladder prototype was manufactured to validate the models and evaluate the concept. An existing mechatronic plate with 4 valves, sensors, and a microprocessor per bladder was used to control bladder deflation. Unfortunately, flow resistance was higher than expected, which prevented the device from creating the desired impact forces. The prototype was then modified by puncturing the bladder walls, and an ankle-foot simulator was used to mimic impact during slip. Unfortunately, dynamics of the system confounded their value. Subsequent experiments focused on a simplified prototype to evaluate whether impact forces could truly be used to improve slip mitigation. The test used a simple piece of rubber to simulate the sole and applied the expected impact force during an ideal deflation using the ankle-foot simulator. Results shown to the right ultimately proved that the required coefficient of friction could be reduced during the impact period, meaning that the underlying concept is valid. Changes in friction coefficient during impact were then incorporated into updated simulations to verify whether the concept should work with bladder deflation. Results analyzed the relationship between the weight of the person, height of the shoe sole bladders, and the resulting slip mitigation, indicating that increased user weight and bladder height should lead to increased slip reduction. The results showed that meaningful velocity reduction could be achieved. Future work should examine improved modeling, lower resistance airflow mechanisms, slip identification, and slip control. Once achieved, human subject studies will lend invaluable insight into how the shoe behaves in correspondence with the complex psychological attributes of the user.